annular link, so it's a continuation. Yes.
Thank you very much for the introduction and for reminding me about the title of my talk. I also forgot it. Thanks everybody for coming, and thanks for the organizers for inviting me to speak here. This talk is based mostly on joint work with Eugene Gorsky. We put a paper on the archive in April which contains everything that I'm going to talk about and a bit more. What else do I need to say? Well, okay, let me just get started. Okay, so I'll just start with setting some notation. So I'll denote by VRN the Argent braid group of type AN-1, so just a usual braid group on n strands. Okay, and I denote by Hn the corresponding Hecke algebra. And the Hecke algebra is obtained from the group algebra of the braid group over the field of rational functions in Q by modding out by the well-known skein relation that looks like this. So I'm drawing generators, the Argent generators of the braid group as crossings, as you're used to. So positive crossing minus negative crossing equals Q minus Q inverse times the oriented resolution. Okay. Okay, and I want to talk about annular links. So I'll consider the HOMFLYPT skein module of the annulus, or more precisely the positive half of the HOMFLYPT skein of the annulus. So what's that? Skein plus of the annulus will be my notation. So what's that? You take the span over the field of rational functions in Q of braid closures modulo the same skein relation. And what do I mean by braid closure? Well, you take a braid, draw it in a little box, theta, and then close it up, but don't close it up in the plane, close it up in an annulus. So I'll indicate working in the annulus, but just putting a puncture in the disk, that is this sheet of paper. Okay, that's the skein. It's called a positive skein of the annulus because everything that I'm considering in here is obtained by closing off braids, all of whose strands are considered as pointing upward. Okay, and an alternative description of this positive half of the HOMFLYPT skein of the annulus is the following. So if you say we focus on braids with n strands, then if we just consider braids with n strands and force the skein relation to hold, we obtain the Hecke algebra on n strands. But if you're in the annulus, you can take parts of your braid, slide them around the annulus, and you get the same elements. So what we have to do is we have to mod out my commutators. Okay, and then because we're not only considering n-strand braids, but braids on an arbitrary number of strands, I just have to take a sum. We're all non-negative integers. And these things don't interact. So the sum is direct. We give this a name. HOMFLYPT skein of the annulus. And let's put positive here because I'm only considering stuff that is oriented this way. Okay, so it's a almost 30-year-old theorem of Turaev that identifies this skein module, which is of course a skein algebra because I'm in the case of the surface, with the algebra of symmetric functions. The skein plus of the annulus is isomorphic to what I call lambda q, so this is the algebra of symmetric functions. Symmetric functions over CP. Okay, so there are many ways to present the algebra of symmetric function. The algebra of symmetric functions has lots of automorphisms. So there are many such isomorphisms, but I want to consider a particular one. So I'm considering the isomorphism that does the following. So elements of the skein of the annulus are represented by linear combinations of braid closures. So if I take the one strand braid in the annulus, that will map to a very simple symmetric function, namely the first elementary symmetric function, which is actually the same thing as the first complete symmetric function, which is actually the same thing as the first power sum symmetric function, which is the same thing as the Schur function corresponding to the one-box Young diagram. Okay? So this is my notation. Elementary symmetric functions, complete symmetric functions, power sum symmetric functions, Schur functions. Okay, that doesn't specify the isomorphism yet. I have to tell you more. So maybe the best way of telling you what kind of isomorphism I'm considering here is by saying that if you take a Jones-Wenzel projector, or somehow the HOMFLY analog of a Jones-Wenzel projector, and you close it up, and this is a thing on n strands, then you will obtain the nth complete symmetric function. Okay? So now that's actually specifying the isomorphism. So the next thing I'm writing down is just to add some notation to the whole thing. So in Anna's and Duell's talks, we saw these thick edges. There were double edges. So I'm considering actually k-fold edges, and I'll just denote them by a little k next to the thing. So such a k-fold edge goes to the kth elementary symmetric polynomial. If you like representation theory and Turaev invariants, then that would be a circle colored by an exterior power representation with exponent k. Okay, and well, just to set a little bit more notation, the complete symmetric function, complete symmetric function, will identify with the Schur function corresponding to a Young diagram with n boxes in a row. And the elementary symmetric polynomial will therefore identify with the Schur function with a column of k boxes corresponding to ek. So if you don't care about HOMFLY stuff, if you're an SL2 person, you can specialize to the Kaufman bracket skein algebra of the annulus by going through this isomorphism, look at this algebra of symmetric functions, and evaluate these symmetric functions on an alphabet of one variable only. Okay, that will kill all these EKs for k greater than 1, and you'll just end up with a polynomial ring, which is known as skein of the annulus. Okay, other questions? Okay. So a slightly more intrinsic description of what this isomorphism does is the following. So, yeah.
Just to follow up on your comments, where do the Chebyshev polynomials?
So Chebyshev polynomial. Okay, so this thing you can alternatively consider. Oh, no. Sorry. Okay, so this Chebyshev polynomials are an SL2 thing. Okay, so if you evaluate the symmetric functions on one variable, power sum symmetric polynomials will turn into Chebyshev polynomials of the first kind. Complete symmetric functions will turn into Chebyshev polynomials of the second kind. Yeah. Those are the two, yeah. Good. Okay, so consider the following. So there's a trace map which does the following thing. It goes from the Hecke algebra n strands into the skein by just closing up elements. And then it goes to this algebra of symmetric functions via the isomorphism that I've just described. And what it does is it's taken an element of the Hecke algebra and it's mapping it to what? Well, it's a sum over partitions of n, or Young diagrams. And then it's taking, so essentially the representation theory of the Hecke algebra is the same as the representation theory of the group algebra of the symmetric group. So if you and irreducible representations are indexed by these Young diagrams or partitions. So you can take the trace of this element x in the representation, irreducible representation labeled by lambda, gives you a number or a scalar in here, and then weigh this by the Schur function corresponding to lambda. Okay. So yeah, so now this isomorphism is compatible with this trace description. So if you plug this up, if you plug this isomorphism here and take the natural closing up trace operation here, this is what you get. Okay. However, this was not the isomorphism that Turaev considered. Turaev considered something else. So maybe, yeah, let me fit this here. Oh, no, let me. Okay, I'll fit it here. Can you see this? This is okay. Okay, so Turaev preferred the following generators. So somehow the generators that I prefer for the skein of the annulus would be either all elementary symmetric functions, or all complete symmetrics, or all parasums, or my preferred basis would be the Schur basis. So what Turaev preferred was algebraically independent generators, where elements of the skein algebra are represented by certain links. And the links look like this. So well, here's the annulus. So you start here, and then you wind a bunch of times around, and then you just come back. Okay. So this is not a braid yet. I haven't drawn any crossing information. But you see, somehow it would be, if you were to consider this as a closure of a braid, you would have one type of crossing each. And for each of them, you get to choose a sign. And it doesn't really matter which ones you choose. So with some choices of crossings, and you have to take such knots, one for each somehow number of strands that you see here. So for n greater or equal to 1. And then, so they give an algebraically independent set of generators. So a basis of the skein is given by monomials in these guys. Okay. So now we have, well, we have interesting. We have two different bases for the skein of the annulus. We have these guys. I will call them. So let me just make some choice of signs here for the crossings. So we'll call these guys Coxeter braids, because they are braid lifts of Coxeter elements of the symmetric group. And so we can, as basis of the skein of the annulus, we have either monomials in such Coxeter braids, or Schur functions, or monomials in E's or H's or P's. So it's, for me, an interesting question to understand the basis change. Or in other words, to compute what symmetric function corresponds to such a Coxeter braid. It's a very basic question. So I want to give an example. So this will be my example sheet here. And luckily, waves have already been introduced, so I can start computing right away. Maybe let me just quickly remind you, I'm considering these diagrams, these little webs, and if I draw these webs where two strands merge and then split apart again, I'll remind you that this is the little web, and it can be interpreted as the Karsten-Lustig. It's the non-trivial Karsten-Lustig basis element in the Hecke algebra on two strands. Just one such thing. In particular, it's a quasi-idempotent. Okay, so let's compute something. Let's compute the the annular invariant of the negative rate lift of the coxeter element on 2 strands. So you see we're getting lazier and lazier. Anna started with the link with 3 crossings, well, with the link with 2 crossings, so I'm down to 1 crossing. Okay, so how does this work? So I have to replace the crossing by some resolutions. So I'll use this guy. And the replacement is locally like this. The crossing goes to minus q times the parallel resolution. So I get 2 concentric circles. And then I just get plus this double H. Okay. So now I can massage this picture and somehow make this double thick edge very long and make the bubble that's on the right here very small. And then we have this relation that such a bubble actually gives a factor of quantum 2 and you can remove it. So that's the same thing as minus q times the 2 concentric circles, which I'll just keep, plus q inverse times a double fat circle. Okay, and now what does the isomorphism do? We have all the ingredients here. So this isomorphism sends this guy to minus q e1 squared, because a single circle goes to e1, and 2 next to each other go to e1 squared, plus q plus q inverse times e2, because a 2-labeled circle goes to e2. Now we can expand e1 squared into e2 plus h2 and get the following thing. Get minus q h2 plus q inverse e2. Or in terms of Schur functions, you get minus q, the Schur function with 2 boxes in a row, plus q inverse, the Schur function with 2 boxes in a column. Okay. Now let me give a more complex example to tell you that it's still quite nice. Where do I put this? I don't want to put it here. Wait. Just start erasing here. So well, let's get a bit more ambitious. Let's take n-1 crossings. So spiral around here. Let's say that these are n parallel strands here. Then it turns out that this goes to a similarly nice expression. And on the so I'm influenced by homological conventions, so I'll start writing on the right. So what do we get? We get q to the 1 minus n times Schur function associated to the Young diagram with n boxes in a column, and this comes with a positive coefficient. Then here we have q to the 3 minus n, a Schur function with corresponding to a hook-shaped Young diagram where 1 box from below here moved into this arm. Well, and then it's an alternating sum of such hook Schurs until at the very end you see minus 1 to the n minus 1, q to the n minus 1, the Schur function corresponding to the diagram with n boxes in a row. Okay, so that's a nice expression. Has anybody seen this before? I mean, it's 30 years old. People must have done this before. Okay, let me know if you can think of something. So in this alternating sum, there are hook-Schur functions. Right? A different way of describing what this is saying it's a plethistically transformed elementary symmetric function. I'll explain what that means. Plethistically transformed elementary symmetric function divided by q by something. So what is this plethism thing?
Is this an entry of the full twist?
Oh,
Is that what you're using?
is this an entry of the full twist? I guess, oh yeah. Yeah, I think so. Yeah, so there seems to be there's certainly a nice relation between operations on symmetric functions and operations on such braids. For example, one can describe what happens if you cut this braid somewhere and insert a full twist. But I'm not going to talk about it. Okay, so what is this plethistic transformation? So recall that the algebra of symmetric function has algebraically independent generators. So the generating set given by the power sum symmetric functions. Okay. So that means that every element I can expand as a linear combination of monomials in power sum symmetric functions. And now this phi is the automorphism of lambda q, which is defined on power sum symmetric functions in the following way. Phi of Pn is q to the minus n minus q to the n times Pn. So it's taking these power sum symmetric functions and it's rescaling them by such a factor, depending on the index. I'll give you an example. I'll give you two examples. One is stupid. So what is phi of E1? Well, E1 is P1. And this is just Q inverse minus Q times P1, which is Q inverse minus Q times E1. So on E1, it just acts by rescaling by this factor. And if we do this entire operation here, if we take, well, such a thing with just one parallel strand, meaning no crossings, and we run through this algorithm, we'll evaluate phi of E1, which is just this, and then we divide by Q inverse minus Q again, so we get E1 compatible with what I said before. Now, an more interesting example. What if I'm computing phi of E2? To compute phi of E2, I first have to expand E2 into a polynomial in P's. So what is that? So that's phi of, how does this work? I guess I get P1 squared minus P2 halves. Okay, now I can apply phi to each of these terms. So I get Q inverse minus Q overall squared, P1 squared, minus Q to the minus 2 minus Q squared, P2 halves. And now I want to rearrange it and expand in terms of sure functions. And if I do that, I get Q inverse minus Q times minus Q s, the thing with two boxes in a row, plus Q inverse the sure function with two boxes in a column. So now if I were to divide by the scalar, well, I just get the invariant of this Coxeter braid. So this is how you compute with these things. Okay, so here are two questions. With Eugene Gorsky. So these questions are addressed in this paper with Eugene. So the first question is, given a sequence of signs of length n minus 1, I'm considering the braid lift of the Coxeter element in Sn, where the signs of the crossings are determined by this string of pluses and minuses. What is this trace valued in symmetric functions of the Coxeter lift determined this is question 1. So here I told you the answer. I didn't prove anything, but I told you the answer what's happening for the negative Coxeter lift. You can ask what happens with all other possible Coxeter lifts. The second question, which was the original motivation for the project, is how does this categorify? So the motivation here is that the categorified HOMFLY skein of the annulus should be closely related to the derived category of coherent sheaves on the Hilbert scheme of points in C2 if you consider n-strand braids. This comes with a lot of structure, a lot more structure than we usually see in annular link homology. And to understand the structure, we want to understand nice generators for these categories. And Turaev tells us that in the decategorified world, these Coxeter braids are really nice generators. So we're looking at the properties of these generators in the categorified setting as well. Okay, so how much time do I have left, just for planning purposes?
I think it's 20 minutes.
20 minutes more.
A little bit more.
Okay, good. Okay, so I could just tell you what the answer is to this, but I'll torture you with a bit of categorification, okay? So before telling you the answer, or unless maybe does anybody know the answer? I'm really curious to know if this has appeared before. Please computer, no? Doesn't ring a bell? They've done some stuff in this direction, that's right, but I'm not sure. H lambda. Yeah, it's getting close. Okay, let me say a little bit about categorification. So now I'll start to tie in with Wells' talk. So let's. I'll just put a little reminder here that this phi here is this plethystic substitution, that definition I've just erased. Okay, so what does it mean to categorify here? Let me tell you the nicest packaging of the answer that I know. So what is annular Hoganov-Rosansky homology? Annular Hoganov-Rosansky homology is a functor from a category A-link plus. The objects here are braid closures in a thickened annulus. The morphisms here are a restricted class of link cobordisms between such braid closures, which somehow preserve that you are the closure of a braid. So let's say closures of braid cobordisms up to isotopy relative to the boundary. So annular Hoganov-Rosansky homology is a functor that takes as input some objects, some morphisms in this category, and what it spits out is something, well, in a homotopy category over a category p hat. And the most important thing that you need to know about this is that its growth-indeed group is isomorphic to lambda q after tensoring with, well, okay, so you first take the growth-indeed group and then you tensor over Laurent polynomials q with CQ, to be precise. So takes annular links, assigns to them chain complexes in some weird category. But if you take somehow isomorphism classes of objects there, you just get symmetric functions. If you take braid cobordism, so surface connecting two braids, it will give you a chain map between the chain complexes, which is well defined up to homotopy. Okay, now I need to explain what p hat is. And my main point will be that p hat is the simplest thing that it could be. So let's start by describing what P is. P is not P hat. P is something different. So to decategorify to the symmetric function ring, I need something that decategorifies to E1. Okay, so this category will have an object that I'll call E. It's a thing that decategorifies to E1. And you should think about it as the essential uncolored circle in the annulus. What will it be? It will be a C-linear category. And linear also implies additive. And then what else structure do we want? We want that this is graded, because after taking this growth group, we want to recover a Q grading here. So I'll put a grading here. I need to be a bit careful where I put this. Okay, and one other thing. So actually, the skein of the algebra the skein of the annulus is an algebra in two different ways. You can use the usual skein algebra multiplication, but you can also glue two annuli inside each other. And actually, it turns out that these operations are the same, but let's distinguish between them anyway. If we want to, so we want this the structure of gluing annuli inside each other to be reflected in the categorification, and that means that we want this thing, this P, to be a monoidal category. We want it to have a tensor product. So I'll put monoidal here. Okay. And it's also supposed to have some morphism, because if it would just have identity morphisms, that would be too boring. So morphisms. So it has a morphism. An endomorphism of E, I'll call it X. It runs from E to E. And you should think about it as a cylinder, cylindrical cobordism on this essential circle which carries a dot. And it's the same dot that appears in Anna's talk and in Noah's talk. Okay, and otherwise, this category doesn't have. So it's more or less the free category generated by this data. So it's the free, graded, strict, monoidal C-linear category which has an object E, and it has a morphism X from E to E. So I'm imposing as little restrictions as possible. And I forgot one thing. So the category of annular links and link cobordisms is actually braided. You can have, if you have two annular links, you can have them fly through each other in two different directions. So this category is braided. So this also, or at least the image of this guy should at least be braided. The simplest possible thing that I could have here, it's a symmetric braiding. And that's the case. So it's a free, graded, strict, symmetric monoidal category. C-linear category with one object. It has one object. You can also have tensor products of these objects corresponding to the circle, and it has one morphism corresponding to the dot on the cylinder. So that's P. And P hat is just the idempotent completion of the Cherubian model. So that's the simplest possible thing that I can actually put there. That seems to be the universal target of annular Kovanov-Rosansky homology functors. So everything that we currently have factors through this guy. Annular Kovanov homology and so on. No, that's not true. Anna is not here. Then it's true. Anna's quantized homology doesn't factor through this guy. Okay. Any questions about this?
Sorry, I need to read what you said. So P hat is core or
That's the Cherubi envelope.
Okay.
It's the idempotent completion.
Okay.
That means, so let me say a little bit about this. That means if you can form E tensor blah 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 blah, lots of copies of E. So say the nth tensor planar of E. And now I can use this symmetric monodal structure to commute the circles. And so I get an action of the symmetric group on n letters, permuting these E's. Okay, and it's C-linear, so that means I actually get an action of, the group algebra of the symmetric group actually includes into the endomorphisms of this guy. Now, if I take a Young symmetrizer in the group algebra of the symmetric group, that will give me an idempotent endomorphism of E. And because I forced my category to be Cherubi complete, that represents an object in P hat. And it turns out that those are all the indecomposable objects. indecomposable objects in P hat are Schur functors of E. So what I've just described is just the process of taking a Schur functor, evaluating it on this object E. And if you take, if you decategorify this by taking the Grothendieck group, you just get the Schur function indexed by the same lambdas. Lambda here is a partition. Okay. Again, time for an example. Well, should I give an example? Yeah, I should give an example. Let me use another piece of paper. This will almost be isomorphic to the computation that I had before. Okay, what is the annular Koganov-Rosansky invariant of this guy? Well, now we get a chain complex, which looks like this. So first we have two concentric circles, and it comes with a gradient shift Q, and there's a differential, which looks like a little saddle, except that it has this membrane in, and it maps to this guy. And now that turns out to be, so now I'll do the same trick that I did before. I slide half of this around. I decompose this guy into two copies of the double thick circle. One is shifted up in Q degree by one is shifted down. And then I'll see, so what this double edge turns out to be is the second antisymmetric Schur functor, so wedge 2 applied to E. So what I'll get here is Q times E tensor E goes to Q plus Q inverse wedge 2 of E. Now decompose E tensor E into wedge 2 plus sim 2, like we always do. So we get, this is isomorphic to Q wedge 2 of E plus Q of sim 2 of E. And now I get some differential. And here I get Q wedge 2 of E plus Q inverse wedge 2 of E. And the only thing that we need to know here, actually, is that this is an identity component between these two copies of Q times wedge 2. And now we use the trick that I learned from Drawer of Gaussian elimination to kill these two summands, and we'll end up with a chain complex that looks like this. So it's Q times S2 of E goes to Q inverse wedge 2 of E. And then you're done. There's nothing else you can do to simplify this further. All right. Now I would like to, question 1 was to describe the annular invariance of all these Coxeter lifts, and proceed to the more ambitious goal of describing all the annular Koganov-Rosansky homologies of such Coxeter lifts. To do this, Eugene and I consider analog of this platistic substitution on the categorical level, which I'll just write down in a moment. Please warn me when something out of time. Okay, so with Eugene, we're found the following thing. So this is a capital phi. It should remind you of the other phi thing. It's not quite the same thing. Okay, so what is it? It's a functor that runs from P hat. P hat is this free symmetric graded monoidals, blah 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 category, into its homotopy category. If you decategorify this, you get lambda q. If you decategorify this, you still get lambda q. And if you take a symmetric function here, Okay, so if you take an object here, apply this thing, then decategorify, and compare this to, well, first decategorifying, starting, and then evaluating. Here, what you see here is this f goes to phi of f, this is the statistic substitution, and then divided by q inverse minus q. So this is downstairs here. What you see is, well, so the trace, the lambda q trace of this negative Coxeter braid was exactly phi of En divided by q inverse minus q. And now upstairs, what we'll see is that the annular Rosansky homology of, well, this negative guy, how do we draw this? Like this, will be just psi evaluated on wedge n of E. So in some sense, this psi realizes the platistic substitution followed by division by this factor. So I won't describe how this works, how this phi works, but I'll say one thing. So to evaluate phi on a Schur factor on E, that's the same thing as evaluating phi on the tensor power of E. And then this turns out to be a representation for the symmetric group on n letters. So if you hit this again with a young idempotent, a young symmetrizer corresponding to partition lambda, you will recover this thing. And I can tell you what phi of E of this tensor power of E is, because that's actually quite beautiful. So phi of E tensor n can be described as a chain complex in the following way. So as a vector space, you get it as follows. So first of all, you take the reflection representation of Sn. You take its exterior algebra, and you tensor this with E tensor n. Okay? So the reflection representation, let's say here, is just an n-1 dimensional vector space. Spanned by, like, say, let's take basis elements, whatever, u1 up to un-1. And then there's a differential on this entire thing. And the differential is determined by sending such a basis element, so ui, to an endomorphism of E tensor n. And well, we said E itself has an endomorphism that is called X. So if I have a tensor power of E, I have n different x's, and I'll just denote them by x's with subscripts. So ui is sent to the endomorphism given by xi minus xi plus 1. So in other words, the thing, this chain complex that you see here is an n-1 dimensional hypercube, and you can think of it as a causal complex for this sequence of elements. How much time do I have left?
5 minutes.
5 minutes, cool. So I can draw a picture of how this complex looks like. Very explicitly. Oh, and we'll give this a name because it looks like a hypercube. Denoted by cube n for the tensor power here. So cube n looks like this. Well, on the far left, I'm ignoring grading shifts here. On the far left, you see an tensor power of E. And then you get some differentials out here. And here you see n-1, direct sum of n-1 such tensor powers of E. And then, well, the cube grows. And in the second to last step, you'll see again n minus 1 direct sum tensor powers of E, and then they map again to a single E tensor n, and the last differential is just given by x1 minus x2, x2 minus x3, up to xn minus 1 minus xn. Okay, so it's this hypercube-like thing. And what do I want to say about it? I want to say that, well, what we've already, so what I've just erased was actually implying that the annular Havana-Posansky homology of this negative Coxeter closure thing is isomorphic to the sign isotypic component of this thing, because this is still an SN representation. And now we can describe what the annular Havana-Posansky homology of an arbitrary Coxeter lift is. So, so this is somehow the answer to question 1. This will imply an answer to question 1. So if we have such a sign sequence, determines two parabolics of Sn. So I'll denote by two parabolic subgroups, W epsilon and W epsilon bar. So these are subgroups of Sn, which are generated by reflections. This guy is the subgroup generated by reflections which receive a plus sign in this sign sequence, and this is the parabolic that's generated by reflections that receive a minus sign in this sequence. So plus 1 and minus 1 signed reflections under epsilon. Now, if I have these two parabolics, I can I can define in the group algebra of the symmetric group a symmetrizer with respect to this parabolic and an anti-symmetrizer with respect to this parabolic. So let's keep this notation. So S epsilon and S epsilon bar are the symmetrizers, respectively anti-symmetrizers in W epsilon or W epsilon bar sitting inside, well, C's here, CSN. And now there's an old theorem of Solomon that says that the group algebra of the symmetric group can be written as a direct sum of left ideals indexed by such sign sequences epsilon. And the left ideals are formed as follows. You just take this and you hit it with the product of this symmetrizer and anti-symmetrizer. Okay. And now I can describe what the annular Havana-Posansky homology of such a Coxeter lift is. So if I take, well, the braid, which is a Coxeter lift determined by the sign sequence, and take its annular closure, compute the annular Havana-Posansky invariant, that's just isomorphic to a piece of this cube, a piece of this huge complex, this cubical complex. You take this cube and you hit it with the same thing here. So this is not quite an idempotent, but you can still hit it with this. And it will cut out this annular Havana-Posansky homology. So this is kind of weird. So if you somehow this says that if you take all possible Coxeter lifts, compute the annular Havana-Posansky homologies, you can piece them together into something extremely nice and regular. This causal complex. Okay, and then there's a consequence, decategorification. It's probably quite related to what Stavros mentioned. And so our main result can be seen as a categorification of this. So how do we do this? So given such a sign sequence, I'll build a ribbon skew Young diagram. So given epsilon, build a thing in the following way. Start with the box. If you see a plus at the start of epsilon, add a box on the left. So say +1, +1, -1, +1. Let's do a very, very small one. So if I see a plus, I put a box on the left. If I see another plus, I put a box on the left. If I see a minus, I put a box below here. If I see a plus, I put a box on the left. That's not a Young diagram, but it can be seen as the difference of two Young diagrams. So call the big one lambda, and the thing that I've taken out mu. And then corresponding to this, there's a skew sure function, S lambda over mu, and well, trace lambda q of sigma n minus 1, epsilon n minus 1, blah, 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 sigma 1, epsilon 1, can be seen as the statistically transformed skew sure function divided by q inverse minus. So that's the decategorification of this result. And there's more, but I'll stop here. Thank you.
Question, comments?
So this is... Sorry.
Yes, yes.
Ongoing. This is arbitrary color.
This is all uncolored.
All uncolored.
Yes.
Okay.
It's all uncolored at the moment. I mean, you expand in terms of colored things, but the input is uncolored. It's a good question what you get if you start with something colored.
So in this case, you work over a field because you're using the Categorical envelope, I guess. If you were using resolution instead of projectors, you work over Z, and you expect that there will be torsion in the categorification, apart from the one that's in the projectors.
Most of this works integrally, but I haven't thought about proportion.
So like the Gaussian elimination to run over fields that all have really an
That's on the nose.
time value.
I think it's just on the nose, but I'm not sure.
One was a question. Let's thank again Paul.